A very good morning, dear honorable guests, ladies and gentlemen, from Bogor, Indonesia. A very warm welcome to you all from me, Sarah Simanjuntak, your Master of Ceremony for this today online international conference. Welcome to the International Conference on Mathematics, Statistics, and Data Science, the year 2020, under the theme Optimal Data Utilization to Reach Brighter Future, that held from November 11 to November 12, 2020. We would like to welcome you and extend our warm welcome to the Honorable Rector of IPB University, Professor Dr. Arif Satria, SPMSI, Distinguished Dean of Faculty of Mathematics and Natural Sciences IPB University, Dr. Insinyur Sri Nurdiati MSc, Head Department of Statistics, Dr. Anang Kurnia MSI, Head Department of Mathematics, Dr. Insinyur Endar Hanugrahani MS, to all of you, the invited speakers, Honorable Professor Eric Schoen from KU Leuven, Belgium, Professor Hisam Lee from University Technology Malaysia, Professor Ken Seng Tan from Nanyang Technology University of Singapore, Professor Pirayut from Kasetsart University of Thailand, Professor Ray Chambers from University of Wollongong, Australia, Dr. Chuan Sen Tan from National University of Singapore, Professor Wataru Sakamoto from Okayama University of Japan, Professor Tony Bahtiar and Dr. Utami Diasya Fitri from IPB University, Indonesia. We welcome you, President of Indonesia Statistical Association, so-called ISI, Dr. Margo Yuwono, Chairman of Statistics Higher Education Forum, so-called Forstat, Dr. Suhartono MSc, Chairman of Indonesian Mathematical Society, Indo-MS, Professor Dr. Basuki Widodo MSc, Chairman of Indonesia Operation Research Association, IORA, Professor Sudrajat Supian, Chairman of ICMSDS 2020, Dr. Agus Muhammad Soleh, to all of you, respected moderators, distinguished leaders of universities, delegations, researchers and scientists, students, all of you participants from Indonesia, Malaysia, Bangladesh, Iran, Nigeria, Australia, and Japan. We are very glad to see you here and appreciate you taking the time and effort to join this conference. And I would like to invite all of us to give a round of applause to Department of Mathematics and Department of Statistics, Faculty of Mathematics and Natural Sciences, IPB University Indonesia, for organizing this beautiful online gathering. Congratulations, Department of Statistics and Mathematics, Faculty of Mathematics and Natural Sciences, IPB University. Honorable guests, students, ladies and gentlemen, through this ICMSDS 2020 conference, the keynote speakers, invited speakers, scientific presenters, and participants will exchange knowledge and information, either strengthen the collaboration on mathematics, statistics, data science, and their application. And in this ICMSDS conference, also will present 128 papers, and to complete this event, there will be several contests. Just a quick reminder of our today's agenda, ladies and gentlemen. In the morning, we will have the opening ceremony. There will be opening remarks from Chairman of ICMSDS 2020, Dean of Faculty of Math and Natural Sciences, and from Rector of IPB University. Either we will have panel session 1 and parallel session 1. And at afternoon, we will have another 2 notable speakers that will share their knowledge and practical sharing through panel session 2, and there also we will have parallel session 2. And without any further ado, to kick off this conference, together we will sing the national anthem of Indonesia, Indonesia Raya. Ladies and gentlemen, let us sing together the great Indonesia. Honorable guests, students, ladies and gentlemen, we are now ready to starting the conference. To know more about the conference we have, we will now show a video to introduce you the ICMSDS 2020. Ladies and gentlemen, please enjoy the video. It is now my privilege to invite Chairman of International Conference on Mathematics, Statistics, and Data Science 2020, Dr. Agus Muhammad Soleh, to welcome all the delegates. Dr. Agus Muhammad Soleh, the floor is yours.
Thank you, Ms. Farah. Assalamualaikum warahmatullahi wabarakatuh. The Honorable Rector ITB University, Professor Arik Satria, the Honorable Dean of Faculty of Mathematics and Natural Sciences, ITB University, Dr. Stay Nurdiati, the Honorable Head of Department Statistics, IPB University, Dr. Anand Kurnia, the Honorable Head of Department of Mathematics, IPB University, Dr. Endar Nugrahani, the Honorable Chairman of Ikatan Statistisi Indonesia, ISI, Dr. Margo Yuwono, the Honorable Chairman of Forum Penyelenggara Pendidikan Tinggi Statistika, Forstam, Dr. Suhartono, the Honorable President of Indonesian Mathematical Society, Indo-MS, Professor Dr. Basuki Widodo, the Honorable Chairman of Indonesia Operation Research Association, IORA, Professor Sudarya Sutia, the Honorable all invited speaker and all participants. Good morning, and please accept our warm greeting from Bogor. Praise and thanks God Almighty for His blessing and gift, so that we can take part in the International Conference on Mathematics, Statistics, and Data Science. This international conference, with the theme Optimal Data Utilization to Reach Brighter Future, was held in collaboration with the Department of Statistics and the Department of Mathematics, IPB University, and supported by 4 organizations: Ikatan Statistisi Indonesia, OIC, Forum Penyelenggara Pendidikan Statistika Indonesia, or FORSAT, Indonesian Mathematical Society, or Indo-MS, and Indonesia Operation Research Association, or IORA. First of all, we would like to share our gratitude to our invited speakers that will share their knowledge and expertise in this very significant conference. Those speakers are from 8 universities in 7 countries as follows: Professor Erik Schoon from KU Leuven, Belgium; Professor Hisham Lee from University Technology Malaysia; Professor Ken Seng Tang from Nanyang Technology University, Singapore; Professor Virayut from Kasetsart University, Thailand; Professor Ray Chambers from University of Wollongong, Australia; Professor Wataru Sakamoto from Okayama University, Japan; Professor Tony Bahtiar from IPB University, Indonesia; Dr. Chuen Seng Tan from National University of Singapore; and Dr. Utamidia Shafitri from IPB University, Indonesia. And secondly, we would like to inform that we received 128 papers from 37 universities and institutions from 6 countries, namely Indonesia, Malaysia, Nigeria, Bangladesh, Iran, and Japan. Selected paper will be published in IOP Publishing Proceedings Journal of Physics, which has indexed by Scopus, and Indonesian Journal of Statistics and its application, which has 3rd ranks nationally accredited. We would like to express our deepest gratitude to the Rector IPB University, Dean of Faculty of Mathematics and Natural Sciences, IPB University, Head of Department of Statistics and Department of Mathematics, IPB University, the Steering Committee, and the Organizing Committee for their support and assistance in the preparation for conducting this conference. We thank to the invited speakers, presenters, prize recipients, reviewers, moderators, and the organization that support these activities, IC, FORSAT, Indo-MS, and IORA, for their involvement and collaboration in this international conference. We hope that this event can strengthen cooperation and networking between researchers, participants, and institutions at the area of statistics, mathematics, and data science. Finally, please apologize for any inconvenience in this conference due to the limitation of the committee. Thank you and enjoy the conference.
Thank you, Dr. Agus, for the forward speech. Ladies and gentlemen, to know more about the organizer of the conference we have, we now will show a video to introduce you Department of Statistics and Department of Mathematics IPB University. Please enjoy the video.
Departemen Statistika IPB menyelenggarakan pendidikan tinggi bidang statistika dan sains data untuk menyiapkan lulusan dengan kemampuan analitik dan komputasi yang mumpuni sehingga mampu bersaing baik pada level nasional maupun internasional. Lulusan Departemen Statistika IPB disiapkan untuk mampu menerjemahkan permasalahan nyata dalam suatu bidang ilmu ke dalam konteks statistika dan sebaliknya mampu menerjemahkan hasil analisis dan kesimpulan yang ditarik secara statistika ke dalam bidang ilmu yang bersangkutan, serta memiliki landasan yang kuat untuk mengembangkan keilmuan dan atau mengikuti pendidikan lanjut dalam bidang statistika atau bidang lain yang memerlukan penguasaan metode kuantitatif yang kuat.
Departemen Statistika IPB mempersiapkan kami, para mahasiswanya, untuk menjadi data scientist yang handal. Di Statistika IPB, kami diberikan bekal mengenai cara mengambil data, menganalisis, sampai menginterpretasikannya. Karena pada sejatinya, semua hal di dunia ini mengandung data, tak terkecuali hal terkecil sekalipun. Oleh karena itu, dengan kemampuan menganalisis data, maka berarti kami siap untuk bersaing di segala bidang. Statistika IPB, there is no statistics without variance.
Departemen Statistika IPB merupakan salah satu departemen terfavorit di Institut Pertanian Bogor. Menjadi bagian dari Departemen Statistika merupakan salah satu pencapaian terbaik dalam diri saya. Pembelajaran yang diberikan di Departemen Statistika terus mengalami pembaharuan seiring dengan berkembangnya zaman, khususnya di era Big Data. Lulusan statistik memiliki potensi tinggi memasuki dunia kerja, because statistic is a sexiest job.
Departemen Matematika IPB mengasuh program studi S1 Matematika dan S2 Matematika Terapan yang sudah terakreditasi A pada BAN PT. Di samping itu, kami juga mengasuh program studi S1 Aktuaria yang merupakan program studi pertama di Indonesia. Kami memiliki visi menjadi lembaga pendidikan tinggi yang reputasinya diakui secara nasional serta internasional, khususnya dalam bidang matematika terapan. Sebagai misi dari departemen kami ingin menjadi institusi pendidikan, penelitian, dan penerapan matematika yang unggul serta menghasilkan lulusan yang dapat berpikir sistematis, logis, mampu menautkan teori dan aplikasi, bersifat komunikatif, dapat bekerja sama dalam tim, beretika, dan meletakkan proses sama pentingnya dengan hasil akhir.
Di Matematika IPB, kita tidak hanya diajarkan menganalisis, mendapatkan solusi dari suatu masalah, mendapatkan sesuatu yang baru, tapi di sini kita juga dilatih untuk bisa menjelaskan kepada orang lain tentang apa yang kita kerjakan, apa yang kita dapatkan, dan solusi apa yang ingin kita tawarkan. Yang tentunya sangat berguna apabila kita terjun ke dunia masyarakat atau dunia pekerjaan.
Departemen Matematika IPB memiliki dua program studi, yaitu pertama program studi matematika dan juga program studi aktuaria. Yang menarik, program studi aktuaria sudah bekerja sama dengan Persatuan Aktuaris Indonesia untuk menyetarakan beberapa mata kuliah untuk ujian profesi aktuaris. Dan teman-teman semua harus tahu jika aktuaris di Indonesia sangatlah sedikit, dan Matematika IPB sudah menjawab tantangan itu. Jadi untuk kalian yang ingin sekali mendapatkan pekerjaan dengan mudah, kalian cocok masuk ke program studi aktuaria Departemen Matematika IPB.
Hello. Ladies and gentlemen, it is now my singular honor to invite Dean of Faculty of Mathematics and Natural Sciences IPB University, Dr. Insinyur Sri Nurdiati MSc for a welcome remarks. Ladies and gentlemen, let us together welcome Dr. Insinyur Sri Nurdiati MSc.
Thank you very much. Bismillahirrahmanirrahim. The Honorable Rector of IPB University, Professor Dr. Arif Satria, the Honorable President of Indonesia Statistical Association, Dr. Margo Yuwono, Chairman of Forstat, Dr. Suhartono, Chairman of Indonesian Mathematics Society, Professor Basuki Widodo, Chairman of Indonesian Operation Research Association, Professor Sudrajat Supian, the Honorable Head of Statistics Department and Head of Mathematics Department, IPB University, all members of Steering Committee, distinguished invited speakers, and all participants of ICMSDS 2020. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin. Allahumma sholli ala Muhammad wa ala ali Muhammad. May peace, mercy, and blessing of Allah be upon Rasulullah SAW and all of us here. Amin. To begin with, let us say grace to the Almighty God as His will that we are gathered today in healthy condition to take part of the International Conference on Mathematics, Statistics, and Data Science 2020. It is a great pleasure for us to welcome you to this international conference, which held by the Department of Statistics in collaboration with the Department of Mathematics, Faculty of Mathematics and Natural Science, IPB University. The scientific meeting is aimed to give opportunity to the mathematicians, statisticians, as well as data scientists to share knowledge and expertise and to strengthen collaboration among institutions involved, and moreover, try to tackle and solve the problem around us. The COVID-19 situation may hinder the physical conference of ICMSDS 2020. As a consequence, we conduct virtual conference rather than physical one. We aim to reduce the risk of COVID-19 exposure. Hence, the conference is still inclusive, and the participants can still attend to disseminate their latest research finding. We do hope that this situation will not reduce your eagerness to participate in ICMSDS 2020 as invited speakers or as participants. The theme for this conference is optimal data utilization to reach better futures. This theme is very relevant as we enter to the new era of big data, where we witness and face massive data resulted from our daily activities. This reality demands us to respond properly how we handle and manage or utilize the big data to reach our better future. We are so happy that this conference has attracted a great interest to scientists and professionals from several countries. There are 9 invited speakers from 7 countries and 128 papers from 7 countries that will make this conference from Asia, Australia, Africa, and Europe. Before closing my remarks, I would like to sincerely thank distinguished invited speakers from Belgium, Australia, Japan, Singapore, Malaysia, Thailand, and Indonesia for sharing their experience and expertise. Their willingness to share knowledge and ideas are highly appreciated here. I also want to express my gratitude and highest appreciation to the Directorate of International Programs of IPB University for their amazing support at this event. I also would like to thank the organizing committee for the excellent efforts in preparing this international conference. And of course, I also thank all participants from Iran, Nigeria, Bangladesh, Australia, Japan, Malaysia, and Indonesia for their valuable time to join this activity. I wish you all of you fruitful discussion, interesting experiences, and challenging findings. Thank you for your attention. God bless you all. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, dear Ibu Sri Nurdiati, for welcoming all the delegates. Ladies and gentlemen, we now either would like to introduce you further about the host of the conference, IPB University, through a video profile. Enjoy this video.
Generasi terbaik bangsa, inilah IPB di masa kini. Generasi terbaik bangsa, inilah IPB di masa kini.
IPB adalah kampus inovasi yang merupakan ladang persemaian yang kondusif bagi generasi milenial untuk menjadi teknopreneur dan sosiopreneur yang selanjutnya diharapkan bisa memberikan kontribusi untuk kemajuan bangsa ini.
Ternyata tren hidroponik itu di Indonesia sendiri semakin meningkat. Akhirnya saya sendiri itu mencetuskan pada 2017 bulan Maret mendirikan City Pump Bogor.
Berawal dari mahasiswa di IPB angkatan 46, sekarang lulus, alhamdulillah sudah bisa menjadi job creator dari 3 orang karyawan, sekarang sudah jadi 350 orang karyawan.
Kita sudah ada di Desa Benteng, dan desa ini merupakan salah satu prototipe dari kegiatan agri sosio. Jadi di sini teman-teman mahasiswa-mahasiswi berkontribusi dengan konsep sosial bisnis.
Dengan revolusi industri 4.0, maka kita dituntut untuk bisa menguasai dan mengaplikasikan teknologi-teknologi baru tersebut untuk kemajuan pertanian Indonesia. Dan IPB punya tanggung jawab besar untuk bisa mengawal proses transformasi ini sehingga pertanian kita menjadi pertanian yang modern.
Di zaman yang serba modern, Institut Pertanian Bogor juga mengikuti perkembangan zaman, di mana pelayanan mahasiswa menjadi lebih mudah karena dilakukan secara online, sehingga dapat dilakukan secara mobile, di mana saja dan kapan saja.
IPB Pertanian Modern, dan Harapan Bangsa.
Sudah diakui secara global.
Teknologi manajemennya sangat kekinian.
Milenial banget.
Lingkungannya nyaman dan termasuk green campus.
Ayo bergabung menjadi agen perubahan untuk Indonesia.
I now humbly would like to invite Rector of IPB University for an opening remarks and to officially open the International Conference on Mathematics, Statistics, and Data Science 2020. Ladies and gentlemen, let us invite Professor Dr. Arif Satria.
Assalamualaikum warahmatullahi wabarakatuh. Honorable President of Indonesia Statistical Association, Chairman of Forum Penyelenggara Pendidikan Tinggi Statistika, Chairman of Indonesian Mathematical Society, Chairman of Indonesia Operation Research Association, Dean of Faculty Mathematics and Natural Science, IBB University, Chairman of International Conference in Mathematics, Statistics, and Data Science. All invited speakers from KU Leuven, from University of Technology Malaysia, Nanyang Technology University, Kasartad University, University of Wollongong, Okayama University, IBB University, National University of Singapore, and all participants from Malaysia, Bangladesh, Iran, Nigeria, Australia, and Japan. It is my great honor and to greet all of you and to particularly extend our warmest welcome, especially to distinguished invited speakers and all participants in International Conference on Mathematics, Statistics, and Data Science 2020. It is organized by Department of Statistics and Department of Mathematics, Faculty of Mathematics and Natural Science, IBB University. Congratulations for the Head of Department of Statistics, Pak Anang, Head of Department of Mathematics, Ibu Endah, and all of Steering and Organizing Committee. Ladies and gentlemen, this conference will be one of the most interesting conferences in 2020, focusing on optimal data utilization to reach brighter future. This conference is organized to be a place for experts and practitioners of mathematics, statistics, analytics, and data science to meet for getting to know each other, to exchange ideas, and to collaborate towards further development. As we can see together in recent year, with so many disruptive technology, such as virtual reality, artificial technology, robotic technology, the Internet of Things, which is each of them generate a lot of data. It can be seen in terms of volume and from various sources. There is a flow of data every time from year, month, day, hour, minute, second, all captured in real time. Data flow is divided into various types, such as numeric, audio data, video data, location data, which all can be recorded. This will have an impact on how we will formulate many things related to new science, new regulations, and so on. People used to say, who controls oil will rule the world. But now, whoever controls big data will rule the world. We can say, data is the new oil. It's not only about the technology, but also change in our mindset so we can change our behavior. With so many data we already have and we will have in the future, we need ways to utilize data or this new oil as optimal as possible to reach brighter future. This conference will provide unique opportunity, exchanging experience, sharing good ideas, in field of mathematics, statistics, and data science in this 4.0 era. On behalf of IBB University, I would like to express my sincere gratitude to our stakeholders, especially for organizing committee who have been working hard to organize and review paper for this conference. Also, we would like to express our gratitude to moderator and invited speakers, and to all participants, last but not least, for your health and fruitful experience. So basically, that is my keynote speech, and by saying Bismillahirrahmanirrahim, the International Conference on Mathematics, Statistics, and Data Science 2020, which is focusing on optimal data utilization to reach brighter future, officially open. I hope this conference will be successful and enjoyable. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Rector of IPB University, for opening the International Conference on Mathematics, Statistics, and Data Science 2020. Ladies and gentlemen, people say moments will fly away. To remembering those, we'll have to freezing them to have the return tickets to the moments. And now we will frame our beautiful moment of today's through the virtual photo session. We would like to invite you all to kindly turn on your camera. So then our committee would like and could take a photo session of all of us. And please give your very best smile. Kindly open all your camera, turn on your camera. And sending us from wherever you are, your beautiful and best smile. Another few seconds. Please stay on your best smile. Okay, thank you very much. Ladies and gentlemen, now it's time for us to go to the mathematics, statistics, and data science matters. We now come to the panel session 1. Two notable invited speakers, Professor Wataru Sakamoto from Okayama University of Japan and Professor Ray Chambers from University of Wollongong, Australia, will share their knowledge and practical sharing through these panel sessions. And the panel session 1 will lead by Dr. Anwar Fitrianto, MSc. Allow me to read his curriculum vitae first. Dr. Anwar Fitrianto is a lecturer from Department of Statistics, Faculty of Mathematics and Natural Sciences, IPB University. His academic qualification is degree from Bachelor, Master of Science, and Doctor of Philosophy from area of specialization of statistics. He received honors and awards, gold medals from Korea Invention Promotion Association in the year 2015. Ladies and gentlemen, let us together now welcome Dr. Anwar Fitrianto.
Okay, hello everyone. I'm Dr. Anwar Fitrianto. I will arrange the plenary session 1 for Prof. Wataru Sakamoto and Ray Chamber in plenary session 1. Thank you, Master of Ceremony, to give time for this plenary session 1. So please welcome ladies and gentlemen, lecturer, postgraduate students, researchers, practitioners, all participants, organizing committee in the plenary session of International Conference on Mathematics, Statistics, and Data Science. So we will arrange this plenary session 1 to have two distinguished experts in their field. First is Professor Wataru Sakamoto from Okayama University, Japan. And then the second one is Professor Raymond or Professor Ray Chamber from University of Wollongong, Australia. So we will arrange our short time with this distinguished expert in very short time for each presenter to share their knowledge. And we will arrange this plenary session 1 to have each presenter to present his research for 45 minutes each. Then we will have a Q&A session after both presenters presented their research. So without further ado, let me read a very brief bibliography of this presenter. The first one is Professor Wataru Sakamoto. He is from Japan, from Graduate School of Environment and Life Science, Okayama University. Then he got his PhD in 1998 in the field of engineering. So his research interest is in non-parametric regression, more specifically in spline smoothing, and then model selection for mixed effect model, and then Bayesian approach to Markov random field, and then of course in a very good field here is cancer mortality analysis. And he will have he will share his research about something very interesting in statistics, that is analysis of disease mapping data, especially in how to detect cluster of higher prevalence, more flexibility. And then for the second presenter is Professor Ray Chamber. So let me read a brief bibliography of Prof. Ray Chamber. He is from University of Wollongong, Australia. He is a honorary professor, professorial fellow at the National Institute for Applied Statistics Research, Australia. He is an elected member of International Statistical Institute and a fellow of American Statistical Association. And he was co-editor-in-chief of the International Statistical Review from 2015 until 2019. And he has been an associate editor for the Journal of Official Statistics, Survey Methodology, the Journal of the Royal Statistical Society, and many other journals. Of course, we will have a very short time for him to share his knowledge. So without further ado, please welcome Professor Okay, hello, can you hear me? Okay, while waiting for Professor to settle the video or audio setting, so maybe I will. So, yeah, Professor Wataru Yakamoto, can you hear me? Yeah, please.
Okay.
Time is yours. Thank you.
Okay, thank you very much for your introduction. Let me share the slide. Can you see my slide?
Yeah, you can see it.
Okay. Thank you very much. I really appreciate your kind invitation to the conference. It's unfortunate that I couldn't visit Indonesia due to the COVID-19 outbreak. But I'm very grateful for this experience. My name is Wataru Sakamoto. I belong to Okayama University, Japan. Just a moment. Okay. Here is my self-introduction. I belong to the Graduate School of Environmental and Life Science, Okayama University. I used to read my research interests when I was a younger researcher, non-parametric regression, spline smoothing, and model selection for mixed effect models. And recently, I'm concerned about. I'm interested in Bayesian approaches to Markov random fields and cancer mortality analysis. Now, Septian Rahadiantro from IPB University is coming to my laboratory as a student. So here is the outline for my talk. First, I briefly introduce analysis of disease mapping data, especially the Bayesian modeling for disease mapping data. The next, I propose two approaches for cluster detection. One is by echelon scan, and the second is clustering with spatially correlated latent variables. And as I give concluding remarks. So, in the analysis of disease mapping data, our interest is to extract meaningful information on the spatial structure from raw spatial data, and then to detect clusters with higher risk of diseases. However, it would be difficult to read such information directly from raw spatial data, which may involve complicated structure with spatial correlation and large variability. So this is a list of characteristics of disease mapping data. Usually, a discrete value is observed for each small area, such as the number of deaths or incidences. Different population or expected frequency for each area is observed. And spatial structure, such as location and adjacencies, available. On the other hand, the assumption of independence does not hold. So, according to the book by Lesafou and Lawson, the methods of disease mapping data analysis is classified into the following. First, searching and detecting clusters, so-called hotspots with higher risk. And the second one is inference on relative risk and ecological analysis. And especially spatial smoothing, in order to make inference on relative risk, spatial smoothing based on using Markov random field is very popular. And the latent Gaussian models by Ru and Held is a flexible tools to extract information behind the spatial structure. The Gaussian Markov random field, GMRF prior, is included is induced on the spatial effect. The spatial in which the GMRF has the sparse adjacency matrix based on neighborhood relationship, and posterior means visualized on a corpus map. The inference in the latent Gaussian models, the inference on parameters are conducted by MCMC sampling from posterior distribution, and also integrated nested Laplace approximation is also used. The latent Gaussian models can also take account of over-dispersion and covariance adjustment. However, in latent Gaussian models, detection of clusters is not considered directly. So there are some issues in existing approaches. First, searching and detecting clusters in searching and detecting clusters with higher risk, it takes much time if shapes of clusters is not restricted, and moreover, the extension of models for covariance and over-dispersion is conducted ad hoc. And on the other hand, to make Bayesian inference on relative risk, it is difficult to interpret the clusters clearly. So in this presentation, we provide two approaches to detect clusters of higher prevalence. The first one, echelons, is the echelon scan based on the estimated spatial effect in the Poisson models with the latent GMRF. The second is the clustering method with spatially correlated categorical latent variables. Okay, so we briefly introduce, we briefly review Bayesian modeling for disease mapping data. Here is a notation. Suppose that study region is separated into any areas. The yi be the number of cases observed in area I. Then mi be at-risk population size in area I, and lambda I be a no relative risk in area I. So we assume the Poisson model for the responses with mean mi lambda I. The maximum likelihood estimator of lambda I becomes standard mortality ratio, but it is not realistic if 0 is observed. So we impose the prior for the relative risk as gamma distribution, and then the posterior distribution for the given y also becomes gamma distribution with posterior mean as follows. So based on this, the empirical base estimator of lambda I is defined as follows, where A hat and B hat are maximum marginal likelihood estimate, which maximizes the likelihood based on the marginal distribution that is extended negative binomial. And next, I explained Markov random field. In the graphical model representation, node corresponds to random variable which are either observed or not. And the link shows dependency between random variables. Markov random field has undirected graphical model representation, and for spatial data, adjacent areas means that the two nodes are linked. For example, on the right graph, x1, x2, the pair x1, x2, and y1, y2 are dependent, but conditionally independent for given z. Okay. Next, as a kind of Markov random field, intrinsic conditional autoregressive ICAR model is often used. The joint density function is represented as the product of normal densities for the difference between adjacent two areas, where tau z is a precision parameter for spatial effect. ICAR model is an intrinsic Gaussian Markov random field. The precision matrix QZ is singular and sparse, and its element corresponding to the pair of non-adjacent area is 0. Given the spatial effect at other regions, Zi conditionally follows the normal distribution with mean the average of spatial effects at adjacent areas, and variance inversely proportional to Ni, the number of regions adjacent to the area I. Next, BYM model. I explain BYM model. Bisak-Yok-Mori BYM model is often applied for disease mapping data. Log relative risk at area I is represented as the sum of covariate effect with regression term, spatial effect, which is correlated with ICAR model, and non-spatial random effect, which is IID. The BYM Bisak-Yok-Mori model belongs to the class of latent Gaussian Markov random field model, which is characterized as follows. Y is a vector of observations, each of which is conditionally independent for given latent variable Zi. Z is the high dimensional vector of latent variables, which has the first order intrinsic Gaussian Markov random field prior. Theta is the hyperparameter vector of relatively lower dimension. Joint posterior distribution of Z and theta for given Y is obtained via Bayes' theorem. The essence of Bayesian inference is marginalization, that is integrating out of uninterested variables. Posterior sampling is Markov chain Monte Carlo is popular, and integrated nested Laplace approximation in La is also proposed. We are mainly interested in obtaining the marginal posterior distribution of each latent variable Zi, which is obtained by marginalizing the joint posterior of Z and theta with respect to the other variables. The marginalization requires high dimensional integration, and the integrated nested Laplace approximation proposed by Roux et al. Provides fast computation without posterior sampling, using Laplace approximation of the posterior distribution of Z and numerical integration on the distribution of theta. It has been shown that INLA has estimation performance comparable to the Markov chain Monte Carlo. Okay, here are some packages for computation. First, STAN is implements Hamiltonian Monte Carlo method, which is a kind of MCMC, and RSAN is an interface for R. The R package SPAM implements MCMC for Gaussian Markov random field. Gives sampling with method processing is conducted. And R package INDA implements INDA. In this presentation, for the first proposal, I use INDA, and for the second proposal, I use STAN. Okay, then we move on. I'm sorry. We move on to the cluster detection problem. In the standard two-phase model on the relative risk to detect a cluster C, we consider the null hypothesis that lambda C equal lambda n for any cluster C versus the alternative hypothesis lambda C is greater than lambda n for some cluster C. The spatial scan statistic based on the likelihood is defined based on the likelihood as the soup of the likelihood ratio. In the likelihood ratio test, the p-value is computed on simulated null distribution, which takes much time because the statistic takes the supremum. So the clusters for which the spatial scan statistic is locally maximized are detected. The circular scan restricts the clusters to be circular shaped. The flexibly shaped scan allows non-circular shaped clusters, but it requires much computational cost. The echelon scan is based on the echelon analysis I will explain in more detail. Echelons represent geographical structure of variation in spatial data. From the spatial data, echelon dendrogram is first created as follows. The echelon consists of some peaks and foundation, and so on. The echelon dendrogram indicates the location relationship among such peaks and foundations. In order to construct echelons, we need observations, observed values, or at least their ranks in each area, and information on neighboring relationship between areas. Echelons constructed from raw data lead to a complicated echelon structure. So an alternative method is to use empirical-based estimates of the relative risk. So in this figure, the red area shows the first peak of echelon correspond to here. And the second peak of echelon is added here. And then a foundation under the peaks is added here. Here is an illustration of the procedure of the echelon scan. Well, first, we choose the top peak of echelons, and we take the highest level area to form an initial cluster C. Say C, then add to C an area which is a neighbor of C in the same peak of C, subsequently in descending order of the level. Next, we choose the second highest peak and form clusters as in step 1, and choose next peak or foundation in descending order and forms clusters as in the previous steps. The scan statistic is computed for each candidate cluster, and clusters for which the statistic is maximized are detected. The echelon scan enables us to deal with clusters of non-circular shape and to detect significant clusters more efficiently. Next, we propose a model-based echelon scan as described below. Fit the Poisson model with a latent GMRF to spatial data and estimate the posterior means. Next, we construct an echelon dendrogram from the posterior means. Next, for each cluster C is scanned on the echelon dendrogram, fit the following Poisson model with a two-phase latent variable and random effect, and obtain the following marginal likelihood. And then we detect clusters C for which the marginal likelihood is maximized. Okay, a justification of using the marginal likelihood can be explained by the Bayes factor. For two candidate clusters C1 and C2, the Bayes factor is defined as the ratio of the marginal likelihood. If we assume that PC1 and equal PC2, then a cluster of larger marginal likelihood should have higher posterior probability. The advantages of the model-based scan are as follows. The posterior means of F1 to Fn are spatially smooth, so the resulting echelons and clusters are expected to have more aggregate shape. And moreover, the extension to the case of covariate adjustment is straightforward. So we need some model selection criterion to choose between the null model and the alternative model with significant clusters detected. Here we use the Debian information criterion. We compare the DIC value for the cluster detected model with the one for the null model. Okay. We applied the proposed method to Germany oral cavity cancer data. For each district, YI, let YI be the number of cases, MI be the offset values proportional to the number of people, and XI be the covariate measuring smoking consumption. The figure shows standard mortality ratio from raw data. We fitted Poisson models with the following three formulas suggested by Martino and Roux. First, A, without covariate effect, B, a linear covariate effect, and C, nonlinear covariate effect. We conducted echelon scan based on the three models on the echelons constructed from the posterior means of Fi. Disjoint clusters giving largest values of the marginal log likelihood ratio were detected. And we also conducted the echelon scan based on empirical based estimates. And furthermore, we applied the circular scan and the flexibly shaped scan. The largest cluster size was restricted to 50 areas. This table shows the number of peaks and foundation in the echelon constructed from the empirical based estimates and those constructed from the posterior means of spatial effect in the latent GMRF models. The latent GMRF models generated less numbers of peaks and foundations than empirical based method, which suggested that the resulting clusters are expected to be more aggregated. And this figure shows the primary cluster with the largest spatial scan statistics detected by the circular scan and the flexibility scan, shaped scan. The areas belonging to the detected cluster were filled in green. And this figure shows the echelon built, echelon built from the empirical base estimates of standardized mortality ratio, and the primary cluster detected by the echelon scan based on empirical base estimates. And this figure shows the echelon built from the model A without covariate effect, and primary cluster detected by the model-based echelon scan. Next, this figure shows the echelon from the model with linear covariate effect, and the primary cluster detected by the model-based echelon scan. It detected the cluster including different areas from those for the model A. I think this is would be affected by the covariate effect. And this figure shows the echelon built from the model with nonlinear covariate effect. Then the primary cluster detected by the model-based echelon scan. And this table shows clusters with smaller p-values detected by the circular scan, flexible scan, flexibility shaped scan, and echelon scan on the empirical base estimates. And this table shows clusters with small p-values. This table shows the clusters with the largest marginal log likelihood ratio detected by the echelon scan in the latent GMRF models. The cluster with the largest marginal log likelihood also provided smallest DIC. The result suggested that the clusters scans from latent GMRF models were reasonable. Moreover, we evaluated the performance of the proposed method by a simple simulation study. We generated 100 replications of data sets of size 100 according to the Poisson model on the square region as follows. And the red region shows the true high risk region. So for each data set, we fit a Poisson model. Echelons were constructed from the posterior means. Echelons were constructed from the posterior means of Fi and from the empirical base estimates of lambda I. And the primary cluster was detected by echelon scan. This table shows percentage that each area was contained in the detected cluster. The echelon scan with empirical base estimates have tendency to detect clusters outside the true high risk region. This table shows the percentage for the latent GMRF model without covariate effect. And this table shows for the latent GMRF model with covariate effect. And this table shows and this model detected the true high risk region most appropriately. So the clusters scanned on the echelons from the latent GMRF model were reasonable. Okay, so next we introduce the second proposal, clustering with spatially correlated latent variables. The mixture model are popular for model-based classification. The categorical latent variable represents the class that an observation belongs to say CI. We define the conditional distribution given the class as F, and the probability of belonging to a class as alpha ik. Then the marginal distribution becomes a mixture distribution as follows. However, we usually impose an assumption that the observations are mutually independent. However, for specialty data, the assumption may not hold. So in previous research, a Poisson mixture model was proposed by Fernandez and Green. They considered as joint posterior as gamma distribution with order restriction. And in their model, spatial modeling for the mixture rate alpha ik, spatial correlation is induced using GMRF. The computation for Bayesian inference is conducted with reversible jump MCMC. The number of components k is also selected. The model in the modeling by Fernandez and Green, posterior mean is constant for each class, but no covariance effect of dispersion is introduced. And they say that it requires computational cost. It requires millions of MCMC sampling. So, and our idea is our idea is clustering with taking account of spatial structure, and we propose a modified BYM model in which the spatial effect is mixture model, and we compute posterior probability of belonging to each class to detect the clusters more objectively. So in our modified BIM model for log relative risk, spatial effect SI at each location is assumed to be constant and conditionally independent, given the categorical latent variable representing a class. Moreover, we assume the probability model for the probability of belonging to a class alpha ik. This is similar to the grouped continuous model by Fernandez and Green, but our model also includes covariate effect and of the non-spatial effect for over dispersion. This figure shows a graphical model representing this figure shows a graphical model representation of the proposal model. Solid arrow shows stochastic dependency, while dashed arrow shows deterministic dependency. If Zi is directly connected to lambda I, this is an ordinary BYM model. Our proposal is the inserted path, red part. The joint posterior distribution of parameters marginalized with respect to the categorical variable Ci is represented as follows. Then the posterior probability belonging to the class is a posterior mean of the following probability, which is obtained with posterior sampling. We use R-stan for posterior sampling. Here is a part of the R-stan code to obtain log posterior density, which is modified from Morris, which is obtained with which is modified from Morris for ordinary BYM model. So we show a simple numerical experiment. We prepare two types of the data set, high prevalence area. The left figure is the high prevalence area at random, and right figure shows the high prevalence area as aggregated. This figure shows the result of clustering under IID assumptions. The number of clusters k is set to 2. Posterior probability for the class with higher risk is displayed. And if high prevalence areas sorry, and the next figure shows the clustering with our proposed method, posterior probability for the class with higher risk. If high prevalence areas are aggregated, the proposed method can detect the areas more clearly than under the IID assumptions. And also, we applied the proposed method to Scotland lip cancer data included in the package, R package. The lip cancer cases and possible covariate risk factors for the period, this period for 56 districts in Scotland. Let yi be the observed number of cases in each district, and mi be the expected number of cases in each district, and xi be the percentage of the workforce in each district employed in agriculture, fishing, and forestry. This figure shows the raw standard mortality ratio, and this figure shows the percentage of the workforce covariates. And we first fit the BYM model, ordinary BYM model with Bayesian inference. We can obtain posterior mean of spatial effect, which varies from -1 to 1.5. And we can see the northern part has higher prevalence. However, it is hard to interpret the estimated spatial effect because it is on natural log scale. Moreover, we cannot find whether the variation of the spatial effect is significant or not. This figure shows the result of clustering with proposed method. The number of clusters k is set to 2. The posterior probability for the class with higher risk is displayed. The posterior probability can provide easier interpretation because this is probability from 0 to 1. It is also possible to divide into 2 regions with some threshold values, such as 0.5. The left figure shows the clustering under IID assumptions, and the right figure shows the cluster under ICAR prior. The proposed method, the right figure, can classify into 2 parts of regions more clearly. This table shows the posterior mean and 95 credible intervals for parameters. We haven't shown here, but if we obtain the credible intervals for the difference between mu1 and mu2, we will be able to judge whether the difference is significant or not. So, as a conclusion, I give concluding remarks. We introduced analysis of disease mapping data. And especially how the method of clustering with the spatial structure to search and detect clusters with higher prevalence. We introduced 2 approaches. The first one was cluster detection by echelon scan using the posterior means of spatial effect estimated with latent GMRF. And we obtained more aggregated echelons and clusters than using empirical-based estimates of relative risk. And the second approach, we introduced the clustering we proposed clustering with spatially correlated categorical latent variables. The categorical latent variable is related with the latent GMRF. The posterior probability provides a cluster more objectively. For future works, especially for the second approach, I think we need to investigate and brush up for the usefulness, including the case k is greater than 2, and more cases and simulation studies. And the second, we need to consider improvement for fast computation. In this presentation, we used RSAN MCMC method, but by combination of INDA and MCMC, we could improve the fast computation. We need to consider, and we next we need to consider the selection of the number of components such as VIC, DIC, WIC, or other non-parametric based methods. Moreover, we would like to apply for special temporal data, such as cancer mortality data in Japan and COVID-19 data, and so on. Here are references for my presentation. That's all. Thank you very much for your kind attention.
Okay. Thank you, Professor Wataru Sakamoto.
Yeah, thank you. So
thank you for
so that lines the
and very valuable time for this conference. Proper Chamber present his
so sorry, I couldn't hear the lines crowded. So should I answer to the question entered in the chat?
Hello. Prof. Wataru Sakamoto, we will have our Q&A session after hearing from Prof. Ray Chamber to present. So we will have our Q&A session after you and Prof. Ray Chamber presented your knowledge. So now we are waiting for Prof. Ray Chamber to present. Prof. Ray Chamber, are you with me?
So sorry, it's difficult to hear in the line.
Yeah.
Sorry.
So Prof. Wataru, maybe you can stop your presentation to have a chance for Prof. Ray Chamber to present his slide. Yeah. Hello.
So
can you hear me?
It's difficult to hear. Sorry.
Okay.
So
yeah.
Is it okay to answer the questions in chat with my entering sending my from me the message?
Okay.
Prof. Wataru, maybe you can
connection problem, I think.
Hello.
Hello. Hi.
Hello.
Yeah.
Yes.
Yes.
Can you hear me?
Yes, but cannot hear clearly.
Okay. Maybe you can now stop your presentation.
Okay. Okay.
Yeah. So we will have our Q&A session after hearing from Prof. Roy Chamber.
Sorry, pardon me. Sorry, pardon me.
Okay. Yeah.
I'm sorry. Pardon me.
Yeah. Okay. Thank you, Mr. Professor Wataru Nakamoto.
Yeah. Thank you very much. Oh.
So hello, right chamber.
Hello. Can you hear me now?
Yeah, I can hear you. Time is yours. You have around 45 minutes to present your research. So
Thank
time
you.
is yours. Okay.
Thank you. I apologize in advance if I make some mistakes. Oh, good. I'm there. Now I need to share a screen. So I will share a screen. And there we go. Can you all see my screen?
Yeah, you can see it.
Okay, good. I will. That's fine. Okay, that should do it. Okay, thank you very much. My thanks to the organizing committee of the IPB University in Bogor and to the people. I was originally hoping to come to Bogor physically for this meeting, but unfortunately things got a little constrained because of the COVID. And it's interesting because I know about the University of Bogor for many years because I used to work at the Bureau of Agricultural Economics in Canberra in Australia. And I think at that stage, I think it was referred to as was it the Bogor Agricultural University or something like that. And many people, I think, from Canberra had gone to Bogor and talked about it. A very beautiful place. And certainly the pictures I saw certainly confirmed that. It's a pity I couldn't get there this time. Okay,
hopefully next time.
Maybe next time. Okay, so what I want to talk about today is some work done over the last few years with colleagues at the University of Pisa in Italy, Gia Bertarelli and Nicola Salvati. Actually, this was coming out in the Italian Statistical Society Journal, Statistical Methods and Applications. But I will show it to you now. So what I want to talk about essentially is dealing with outliers in business survey data. And it was interesting because I was thinking about it in terms of Bogor, and a lot of my interest in this area started when I was working in agricultural economics, dealing with farm data, and often had to deal with outliers. And farm data is a type of business survey data. We were dealing in economic data collected from farms. So in some sense, there is a connection to a lot of the work that goes on in Bogor here. And hopefully my talk will resonate with some of you. But generally, outliers and samples are pretty common in business and income surveys. And there's often, usually they're corrected before processing of the data. And that's not controversial if these outliers are due to errors in the data. But in many cases, the outlier is not due to an error in the data. It is an actual correct value. And then that is a situation that's of interest to me. Because when you see something that is correct, is verified, and is in a sample, then you have to ask yourself, what about the units in the population that I didn't see? How many of them are like this outlier? We refer to those type of correct, if you want to call it, sample outliers as representative. They represent, in some sort of sense, outlying behavior in the rest of the population. Now, you can deal with outliers. You have some model, perhaps, for your population that you've drawn the sample from. And you could use outlier robust estimation methods with your sample data. That will effectively exclude the outlier from any sort of inference in terms of or parameter estimation. And then you can make predictions for the non-sampled values on the basis of your outlier robust fit. We refer to this as a projection type approach, because what you do is you take a working model, which is essentially nothing to do with outliers, You estimate or fit that working model using robust methods applied to your sample data, and then you project that working model onto the non-sample part of the population. But of course, if you have representative outliers, this immediately says you must be biased, because there are some non-sample units, or at least there could be, which won't fit this working model. So we need an additional bias correction term. That's the outlier situation. Now, what I want to combine that is with small area estimation or domain estimation, where we're dealing with the situation where we are dealing with small samples. I'm typically referred to as small areas, but it doesn't have to be small areas. It can just be small groups in the population. And the outlier problem can be much greater in these small groups. I mean, a single outlier in the sample from a domain will have a much larger relative impact on inference about that domain compared to that same outlier in a much larger population sample. So, you know, small outliers in small area estimation are particularly bad to have. So what I want to do is I want to explore domain level or small area level implementation of outlier robust model fitting and combined with some form of partial bias correction. And I'll compare what I call a predictive strategy with a projective strategy. I've already talked about projection, but predictive is when you put a bias correction in. It will show that robust predictive estimators are less biased than robust projective estimators. They're not unbiased, but they are less biased. But the price you pay for this correction is higher variability. And,
sorry, Prof. Your slide is not moving.
That's all right, because I'm still here. Can you, I'm trying to go backwards. Okay. Did my slide move? Did my slide move just then?
Yes, still displaying not yet, Prof.
No, it's not moving. Okay. I'm just thinking of why it isn't moving.
Not moving yet.
So I'm coming out of full screen projection now.
Not moving.
Now it's moving? Okay, that's fine. No problem.
Yes.
These things happen. Perhaps better to stay out of full screen. That way I know what's going on. Okay. So anyway, the point I'm trying to make is mean squared error estimation in this situation can be very difficult. And there are bootstrap methods and also analytic methods based on linearization. And we've published some papers on that, and I'll mention them briefly. Okay, so put this in context. I want to use an actual business survey. Well, actual as much as possible, because often business survey data are highly confidential. But there was a project called the UREDIT project that was conducted 10, 15 years ago in Europe, funded by the EU, which was looking at how to deal with outliers in business surveys. It was called UREDIT. And part of that, the UK National Statistics Office, the ONS, they had something called an annual business inquiry, a survey. They actually took data from that annual business inquiry and effectively recreated it for use in this UREDIT project. So ABI, or annual business inquiry data, very realistic, was part of the UREDIT project. There were 6,099 sample points. They were classified, these are businesses, they were classified into 28 classes, type of industry classification, with sample sizes ranging from 9 to just over 1,500. So huge variation in class sample sizes. There was an auxiliary variable, something which was known for everybody in the population, which was a register value of the turnover of the business, which is referred to as turn reg over here. And there were many, many output variables. 5 of the most important are listed on this slide, but the one in red called tax dot, or total taxes paid, is the one I'm going to pay attention to. My comments would apply to the others as well, but I just pick one of them. And I'm also going to restrict because otherwise the pictures are impossible to see because everything is so skewed. I'm going to restrict to situations where the business has actually paid some tax, so tax dot is greater than 0, and also where turn reg is less than 100,000, because there were some businesses, a very few of them, with huge values for turn reg, and if you leave them in there, you can't actually see anything on the plots. And that brings the sample size down to 5,554. And with the class level sample sizes ranging between 7 and 1,489. And the target is estimation of the population mean of tax dot at each level of class. So it is a small area estimation problem, but with a highly skewed data set. Okay, so here's a plot just showing you, sort of illustrating how skewed it can be, how variable. This shows a plot of tax dot versus turn reg. Tax dot is on the vertical axis, turn reg is on the horizontal axis. The plot on the left is the all 5,554 sample units with different classes with different plotting symbols. And the plot on the right is a much restricted area of that plot, essentially the bottom left-hand corner blown up. And you can see it's even in there, there's a huge number of units and a huge amount of variability, many outliers in here. Just to illustrate, you got observations over here, which are clearly quite discordant compared to what's going on down here. This is just a quick plot showing you for some of the classes, what the data look like. I don't know if you can see it, but there's a horizontal dotted line and a vertical dotted line, which shows you the sample average in each of these class groups. You can see sometimes there seem to be a large number of points, and then down here, there's very few points, and you've got points like one up there and one down here. So you have the outlier problem can be quite substantial with these data. Okay, so in order to deal with this, I'm going to basically create some notation, and then we'll go into it. So I'm going to assume areas, or in my case, classes, are indexed by I, and units or businesses within those areas are indexed by J. And the variable of interest is going to be Yij, and the target parameter is going to be the area average or mean, Y bar I. Now, small here means small sample sizes. So Ni, which is the sample size in area I, is going to assume to be a small number. Now, we have a working model for the conditional distribution of Y given our auxiliaries, which I'm going to denote by X. And that working model allows for between and within area variability for Y, which we modeled by area and unit level random effects. And we're going to assume that the method of sampling is non-informative. So, for example, some form of random stratified sampling is used. So non-sample units have the same conditional distribution as sample population units. Okay, so the classic estimator in this situation, and the one you'll find in textbooks or books on monographs on small area estimation, is the so-called a random intercepts model. And it's the EBLUP, or empirical best linear unbiased predictor, with the PR denoted here, which is the Prasad-Rao method of mean squared error estimation. So as you can see over here, the working model is a linear mixed model. You've got Yij, you've got some fixed effects there which depend on your auxiliaries. You have an area random effect and an individual random effect. And you have all the usual assumptions, which I've denoted here as the area effects are IID with a 0 mean and a variance sigma squared U. And the individual effects are also IID with 0 expected value and variance sigma squared E. And U and E, in the area effects and the individual effects are uncorrelated or conditionally independent of one another. And so you can write down the covariance for the observation, this vector of observations Yi, which is the individual's values inside area I, and that will have the typical block structure that you see in this sort of situation. Over here, this is the identity matrix of order cap Ni, And this is obviously a matrix of order cap ni by cap ni, which is just contains ones, because this is just a vector of ones. And the empirical best linear unbiased predictor, it's quite straightforward to write it down, is just obviously the average over the population size of the small area. First of all the observations that you saw in your sample, sum them up. And then for those units that you didn't see in your sample, which you denote by U/SI, UI/SI, this is units in area I, which are not in a sample. Then what we do is we predict their values as the X times our estimate of beta, the fixed effects, or the predicted or the estimated fixed effects, plus the predicted random effect for that area. Just to note that by Y hat I over J. And mean square error estimation is via a linearization based PR, Prasad and Rao, or parametric bootstrap often gets used here as well. Now, with outliers, what you have to do is take this and robustify it. And typically what's done is taken an M estimation approach. So you essentially look at estimating equations and you make sure that individual components of the estimating equation for parameters do not make too significant, do not to have too significant an effect on the solution of the estimating equation. So for example, the robust M estimating equation for beta over here is the standard one, but what you have here is this function cap psi, which is applied to standardized residuals. And what that does, that function does, is it says, okay, if the standardized residual is small, leave it alone. But if that standardized residual gets too big, then you truncate it. And so that's often referred to as the influence function for the M estimation procedure. Similarly, you got robust M estimating equations for the variance components of your model. I won't try and interpret this here. It's essentially applying the same idea, but to the maximum likelihood estimating equations for the variance components. It's referred to as MLE2 method, Richardson and Welch, 1995. And then you use the method of Fellner, 1986. So you get your estimates of beta and your variance components out of the solution of those two equations. Then you put them into estimating the random effects, and then you put that together. Effectively, you just replace the beta hat in the BLUP by the robust estimate of beta, and you replace the U hat I in the eBLUP by the robust estimate of it. And this we refer to as a robust projective estimate. It was published by Sinha and Rao in 2009. And again, you can see it's projective because it basically is saying that the mixed model, I'm assuming for most of the population or most of the units in that area, applies to everybody who I didn't see in that area. MSE estimation, difficult, very difficult for this particular estimator. As a linearization-based estimator, which Nico Salvati worked on, we published together in a paper in JRSSB, and it is complicated. I'm not going to go into great detail about it, but it contains components, as you can see over here, which can come from contribution due to the robust estimation of the fixed and random effects, components associated with the prediction, and also components associated with robust estimation of the variance components. In that sense, it reflects a similar decomposition that the Prasad Rao estimator has, but these H things over here are somewhat more complicated. Okay, so we need to get away from projective estimators to estimators that can actually handle representative outliers. And so we need to have some sort of correction for the bias in our prediction for the non-sample units in the population. Because clearly that, if you go backwards over here, you can see that this predictive thing over here assumes that everybody in the non-sample part of the small area or the group is effectively follows the linear model that the same linear model as the good units, the non-outlier units follow in my sample. And that's obviously not going to be true if you have representative outliers. So there, Welch and Ronchetti in 1998 described a way of looking at outlier robust distribution. DF here stands for distribution function estimator. So here you're looking not just at the average value of Y, but you're looking at the distribution of Y in a small area. And they wrote the empirical distribution function in that small area in this, their estimate in this form. This is an indicator function. So depending on this T, which is just the index for the distribution function. So this will just be just the 1 or 0. And over here, you'll have the expected value of the indicator function, which is a probability. And here are estimates of that probability. And the main thing about the Welch and Ronchetti approach is it, in order to estimate, basically, it didn't just try and put the, replace these Ys by their predictive values. It also put a correction in. So to allow for the fact that if you only use predicted values over here, that'll be a biased estimator of the actual probability because it doesn't include any individual variation. So they put in over here a smearing correction for individual variation. And the main thing about this correction is it depends on a second influence function. This here over here is cap phi. And that influence function is not as severe, not as restrictive as the influence function that you used in the estimation of your parameters of your model. Then you can integrate this outlier robust distribution function estimator to get the mean that it generates. And that leads to effectively the Sinai-Rao estimator plus a bias correction, a robust bias correction. And you can do MSE estimation via a linearization-based approach. Now, there's some numerical issues associated with the Sinai-Rao-based predictors, including the one I've just mentioned with the bias correction. It's quite complex to fit the algorithms are quite complex to program. There is, because of the outliers, there can be bias in the estimation of the variance components because you're bounding variability. And so variance components will be biased, or estimates of variance components will be biased. There are often convergence issues if there are many outliers in your data with these algorithms. And probably the one that really is quite difficult to deal with is the speed, especially in any realistic application, is the speed of execution. Just to give you some example over here, LME is a very standard package that gets used to fit linear mixed models with a sample size, say, equivalent to the one we're using in an example. It will fit a linear mixed model to that in 0.001 of a second. On the other hand, RLMER, which is the implementation of the SRR model fitting algorithm, takes 6.8 seconds. So a huge, huge increase in time. QRLM over here is an alternative approach to this, but that's the quantile-based approach, which I'll shortly talk about. That actually is much, much, much faster, as you'll see. And as I sort of hinted at, but it's actually quite clear once you read the literature on this, MSE estimation for these predicted estimated averages within the small groups can be very, very complex. All right, so I want to go on to an alternative approach over here, which is using what we call M-quantile models. This is really an alternative way of characterizing, if you want to call it group variability or group heteroscedasticity in data. You can, obviously the mixed models characterize that basically through a latent random effect, which is the area effect. But you can also characterize that variability in a slightly different way through what are called the M-quantile type models. And just to illustrate just where this is coming from, I just want to point, regression models are just models for a conditional mean. They're just models for the expected value of Y, the thing you're interested in, given X, the covariates that you know. And mixed models extend this to the expected value of Y given X, plus some group membership information. But we don't have to model conditional means. We can, for example, model a conditional median. And more generally, we can model a conditional quantile. And that leads to quantile regression. Goes back a long time, Ponker and Bassett in 1978. Now, that generalization from medians to quantiles is not specific to medians. You can take expectations or means, conditional expectations, and generalize them to the equivalent of a quantile for an expectation, which is called an expectile. And that's Newey and Powell in 1987. So you can have conditional expectiles, you can have conditional quantiles. And then more generally still, oops, sorry about that, you can look at something we call an M quantile, which lies between these two things, the conditional quantile and the conditional expectile. That was work I published with Jens Breckling in 1988. Okay, so the main thing about these models, and this is tied into their ability to characterize sort of group variability, is their ensemble models. So you have a quantile index, Q, which lies between 0 and 1, as everybody knows. And you have an estimating equation over here for this is the M quantile, which is the compromise between the expectile and the ordinary quantile. And this over here is the influence function for the quantile with the index Q. Remember, Q goes between 0 and 1. And that psi Q is effectively a standard influence function multiplied by if you want to call it a quantile function. And this is nothing more than Q times an indicator for whether the T over here, function value is greater than 0, or 1 minus Q, T is less than 0. What this does is makes this ordinary influence functions are symmetric about 0. It makes it asymmetric. If you make the psi function equal to the identity function, you end up with the expectile. If you make it equal to the sign function, you end up with the quantile. And the M quantile takes the average or a compromise between the two. If you put Q equal 0.5, you end up with a central value. So that would be the mean or the median or the M mean. And a linear M quantile just says that for any value of Q, the M quantile at X for Y of index Q is just Xi times beta, where beta depends on Q. And solving this particular estimating equation up here is very, very fast. You can do it by iteratively reweighted least squares, and that's the QRLM algorithm I referred to earlier. This is a picture just showing you the M quantile fits to the data, the business survey data and the API. Q varying from 0.005 to 0.995. Each of these lines along here is an M quantile fit going along here. And you can see that they tend to be more squished at the bottom, closer together at the bottom and spreading more and more. This is characteristic of data which are highly, highly right skewed. So as you get further into the upper, into the right tails of the distribution, the quantiles become further and further apart. Just to illustrate, the red dotted line over there is effectively the OLS line through this data set, and it lies between Q equal 0.8 and Q equal 2. Bless you. Okay, so how do we use this for M quantile models? This is a crucial observation. This gives you an alternative to mixed models. If there are area effects and observations from the same area will tend to cluster together in the support of the conditional distribution or conditional density of Y given X. And if they cluster together in that support, they'll have similar, what we call Q indices associated with their Y values. The Q index of an observation is very simply the value of Qij over here, which essentially equates a particular quantile line with the actual value you see. So every value will lie on one and only one quantile line. You all right? Sir, I'm getting someone's noise talking.
Sorry for that.
That's okay.
Okay.
Is everything okay?
Yeah, it's okay,
All right.
Prof. Yeah.
Okay. So what you do is you solve this identity. You can solve to get an estimate of Q. Effectively, what you do is you find the value of Q such that the value of the observed value of Y lies on that M quantile line with index Q. And that will depend on the influence function psi of the M quantile. Then if you've got observations which are in an area, then all you do is you average these individual Q indices. All right, so it'll depend on the population values of the Y for that area. If they are spread all over the place, then obviously we'll end up with a Q and a Q index of that area, which is very close to 0.5. On the other hand, if these population values tend to be in one part of the support, for example, let's suppose they're in the upper tails of the support, then you'll get a Q index which is greater than 0.5. On the other hand, if they are in the left part of the support, you'll end up with a Q index which is less than 0.5. So this is how you characterize, and this is equivalent to a random effect in effect for that particular area. Okay, so it's just another way of indexing what makes these areas different from one another. Okay, so the thing about it is the Q index for area I leads to a predictive model, because all we have to do now is say, okay, let's just take the average, the Q index for that area. Let's look at the M quantile fit for that Q index and then use that to predict Y in that area. And this is what I did with Nikosavidis in 2006. So you end up this MQ, or the M quantile estimator for an average for an area. Again, you can use MSE estimation via a linearization type argument. This is showing you over here. The main thing about the MQ is it is not unbiased. It has a bias, as you can see over here. So there is a bias term over here which needs to be picked up, which makes this particular MSE estimator somewhat unstable. But the main thing to think about MQ is it unlike the E-blob, where if the actual model is true, then it is by definition certainly unbiased, or the blob is unbiased, whereas the MQ will not be unbiased, but it will characterize different areas. But you can correct that bias. So this is MQB plus CST. MQ is a projective estimator based on a heteroscedastic linear model. You can see that because you can write if you want to call it, the actual value of Y, which we by definition is X times beta Qij. We can write that BQij as the area BQ plus a deviation. And that gives you effectively some variability within an area for individual slopes. And you can show that it must be biased because it is the mean functional defined by a biased distributional function estimator. And that's because the distributional function estimator estimates the probability, the contribution of probabilities by essentially fixed values or fitted values. There's no allowance here for variation within an area. So again, you can use the same sort of bias correction approach we used before for SR to get this, what we call MQB. They have SR and SRB. Here is MQ and MQB, B standing for bias correction. And here's the bias correction term over here in red. So MQB is the MQ, original MQ, plus a correction term. Wrote it up some years ago now. Just again, remember that MQ itself, the M quantile estimator, depends on a influence function and say psi, and the bias correction term depends on another influence function, phi, which is in some sense less extreme than the one that MQ is using. Okay, so just some model-based simulation results. We did a lot of simulations over here. This is just showing you the simulated data. We had heteroscedastic individual errors. We had errors both in the area effects as well as errors in the outliers in the individual effects. So we had outliers in the area effects, outliers in the individual effects. We had heteroscedasticity. And so we had lots of not very nice sort of distributions here to deal with. The one I'm going to focus is the one in the middle, just to show you some results for that, which has both a medium level, a medium amount of heteroscedasticity and a medium amount of errors, both in the area effects and the individual effects. So there were 40 areas. Each area had 500 size population in it. Sample of size 10 was taken from each area. There was medium heteroscedasticity. We used a particular type of heteroscedasticity model called a gamma model. The level 2 errors, which is the errors, the area effects, had 10% outliers in them. And the outliers were shifted. So these are not symmetric outliers. They're shifted. So their expected value over here is not 0. Similarly, with the level 1 errors, there were 3% of those were outliers, and they were also shifted. So we had both, we had outliers, and these weren't symmetric outliers, they were asymmetric outliers. We used tuning constants for k equals 1.345 for psi, which defines the MQ estimators, and 3 for phi, which is the bias correction. Actually, this is probably a small value for that. Bigger values would have probably done better. I also use something called Huberized residuals in something I'm going to talk about shortly, which is a bounded block bootstrap. I'll put that to one side for the moment. I'm going to show you the result. Oops, show you the results over here. So here we have the results for the estimation of means. So this is the median over the 40 areas of the relative bias in percentage terms. This is the median, again, over the 40 areas of the relative root mean squared error. This is for the E-blub. This is for the Sinar-Rao estimator. This is for the bias-corrected Sinar-Rao estimator. Here's the MQ estimator, and there's the bias-corrected MQ estimator. You can look through that, and you can clearly see that, yes, there's biases being corrected, but not completely. The MQ has more bias than the others. But again, that is corrected by the bias correction. But the price you pay when you do bias correction is you see your relative root mean squared error increase. What about when you are looking at mean squared error estimation? Here I'm looking at the relative bias, the median relative bias in mean squared error estimation, as well as the coverage, because this is quite interesting. So you're looking at a nominal 95% coverage, confidence intervals, and in fact what the actual coverage was. And you can see going over here that these are all the linearization-based estimators, both for Sinar and Rao, SRB, MQ, and MQB. You can see that when you have the bias correction in here, you get better mean squared error estimators, and you get better coverage. So the PR estimator here, which is the standard Prasad Rao, its median relative bias is fine and its coverage is fine. But once you start using robust estimators over here, you've got to watch out. So by the way, this may look all right, but if you look up here, remember the original estimator itself was the worst. So you have the worst estimator with the best MSC estimation properties. And that you then have the bounded block bootstrap, which I'll come to, but that actually does very well indeed, both in terms of, certainly here, in terms of the MQB. Very small median relative bias, and very, very good coverage. And that applies here as well. Small bias and reasonable, not wonderful, relative root mean squared error. Okay, so now I've got another 10 minutes or so, so I just want to talk about bootstrap estimation of MSCs. Parametric bootstrap, most people know, you just generate your errors. and generate your bootstrap by generating the errors in it. You can do a non-parametric bootstrap by resampling sort of from level 1 and level 2 sample residuals. You can also do robust bootstrapping. The trouble is when you're doing bootstrapping, you robustify things, you're going to get bias in your bootstrap. You also have typically heteroscedastic data. Now, the random effects block bootstrap is an attempt to get around that. It allows arbitrary level 1 error distributions, but assumes exchangeability at level 2. This is a paper I published in 2013 with Hukam Chandra. The bounded block bootstrap is reasonably straightforward. What it does is it takes level 1 and level 2 working model residuals and bounds them or Huberizes them. And then uses a block bootstrap resampling procedure applied to these Huberized level 1 and level 2 residuals to actually generate a population which has the right amount of level 1 and level 2 variability. And here are the bounding steps. Again, I'm not going to go through them. Obviously, these slides will be available to people if they're interested in them. It goes through the steps over here of how you do it. It's not difficult to do. You can run it now. And then you have the block bootstrap steps, which what this does is generate both level 1 and level 2 residuals appropriately corrected, and then resamples those, and then generates a population. From the population, redraws a sample, and then redraws, and then recalculates all your estimates from the bootstrap sample. Okay, so that's basically what's going on over here. The percentile method is used to calculate confidence intervals. Reasonably straightforward bootstrap idea. All right, so my final thing is just to show you how this works with the ABI. I'm going to just show you effectively what we needed a synthetic population for this, so we just bootstrapped the ABI sample to create the synthetic population. We then had the direct estimate, and because of the way we created it, this is essentially the synthetic population mean, so they shouldn't be viewed as the actual direct estimator, which would be highly variable. The EBLUP was calculated within each level of class. EBLUP estimates for classes 3, 71, and 72 were negative, with extremely high estimated RSCs, which means that we were pretty useless. Over here we see the direct versus EBLUP estimates for the ABI sample, and over here we see the direct versus the EBLUP standard errors. You can see that the EBLUP standard errors, which are going all along over here, are very, very unstable. The estimated EBLUP relative standard errors for over half of the 28 class groups were greater than the corresponding direct relative standard errors. So really, really, the EBLUPs are finding it very difficult to deal with this particular population. We then looked at the Sinha-Rao estimates for this ABI sample, and they were even worse. The Sinha-Rao estimates basically all were around 0, all along here, whereas the actual values were nowhere near 0. So you had this very strange looking sort of arrangement. So the algorithm used to calculate the Sinha-Rao estimates often failed to converge with these data. And even when it did converge, the estimates were substantially smaller, as you can see over here, than the direct estimates. So we went to the M-quantile idea and see if that would work better. It did. Here showing you the M-quantile lines fitted to the data. You can see why you have problems with the fitting a mixed model of these data, because that dotted line right at the top is the actual mixed model fit to those data, the fixed effects, and that is completely out of the main distribution of the data. So there's no surprise that we ended up not working very well. This is another thing showing you the MQ estimates and the estimated RSC of the MQ using the linearization-based estimator against the corresponding direct values, much better looking relationship. And the same thing with the bias-corrected one, similar sort of relationship. There are some obvious differences over here. There are 1, 2, 3, 4, 5 classes where things appear to be rather different, but generally things are falling in line. There was some evidence of shrinkage. There were, as I said, 5 class values for which the MQ, MQB, and direct estimators were notably different. If we look at the estimated RSCs for the MQ, they were less than the estimated RSCs of the direct in 15 out of the 28 class groups. And when you went to the bias corrected one, that's much better still, 21 out of the 28 class groups, your estimated RSCs were better. So there's some evidence that the bias correction used in MQB improves the performance of the MQ estimator. How did we also did the block bootstrap with the thing with the ABI data, but we did it at the log scale because most economic variables behave multiplicatively. So this we modeled it as linear on the log scale. We then implemented BBB using M-quantile models of the log scale ABI data. Then we exponentiated that to generate the population and then did the block bootstrap on that. This is just showing you the log scale M-quantile ensemble fit to the turn reg versus DAX dot. Outliers are still evident, so bounding step is still necessary. Same similar pictures here, showing you the log scale bounded boot compared with the estimated RSCs generated by direct. If you look at the log scale, the MQ and MQB, the MQB tends to be the one that gives you the MQ, and that's MQB, tends to be the one that lines up best. So we did a design-based simulation using ABI synthetic population. This is my, I think, final slide over here. And we look at median relative bias and median relative root mean squared errors. If you look at all classes, remember there were, I think, 28 of them, some of them with huge sample sizes, then you can see that there are issues with the robust estimators. But if you restrict yourself to classes which are very small samples, so the class sample size is less than 50, then you can see the advantage of using the robust estimators very clearly. Big reduction. The EBLAP has huge relative mean squared errors, whereas the robust estimators drop that a lot. Same thing applies when you're looking at coverage. In fact, there's a lot of over coverage over here with the robust procedures. Some final comments. M-quantile modeling is fast and stable, offers a practical approach to robust small area estimation for highly heteroscedastic populations that are the focus in business surveys, particularly as sample sizes get small. The bias correction works reasonably well, still imperfectly in our simulations. The CSD linearization mean squared error estimator has a downward bias as we expect, so has problems with undercoverage. The bounded block bootstrap, on the other hand, seems to work quite well. There's a certain amount of positive bias as the heteroscedasticity increases. It certainly overcovers rather than undercovers. That is an issue, but maybe in practice, that's not so much of an issue. Better to have overcoverage than undercoverage, you know, confidence intervals which are slightly wider than they need to be. And thank you. Any comments and questions? I'm very happy to tackle. So I think I need to stop sharing this. Okay. I'm trying to find, here we are. You are screen sharing, stop share. There we are. I've stopped sharing now. Now I think I need to mute and leave the other people to talk.
Yeah. Okay, thank you very much, Professor Roy Chambers, for the talk. For waiting Mr. Anwar to join again because they have a he has a problem connection. I will allow several participants to give some question. Please, for the first time, Miss Aswi, could you unmute your microphone and mention your question directly to Professor Sakamoto or Professor Rai Chambers. Please, Ibu Aswi.
Can you hear me clearly?
I can hear you.
Okay, thank you very much. My first question is for Mr. Watawaru Sakamoto.
Okay.
So
Hi.
I have applied actually localized model and it's allow for many clusters. So in your slide, how many clusters can be formed? Because I saw in the result that all three models that you apply only have 2 clusters. My second question for Prof. Ray Camber, model by simulation that you apply use only 14 areas, which is relatively small number of areas. Will the result be the same or consistent if applied to a large number of areas? Thank you very much.
Okay, thank you,
The
Mr. Aswi.
first
I
question is
will.
for me, and the second question is for Professor Chambers, isn't it? Both for me.
Pardon, Professor Sakamoto.
It is the first question for me, and the second question for Professor Chambers. Okay, okay.
Yes. You can answer the first question.
Okay.
Please, Pak. Please, Mr. Sakamoto.
For the first question, yes, in today's presentation, I only provided example with the 2 clusters, but theoretically, it is possible to apply to 3 or more clusters because this is a modification of the mixture models. But however, I have tried in the for the Scotland lip cancer data for 3 clusters, but it is difficult to control the priors, the parameter for priors. So and the MCMC convergence, I couldn't get satisfied MCMC convergence. So yeah, and that I would like to investigate the more stable estimation with MCMC or other the combination with INDA. Is this answers your question? Okay.
Okay, thank you, Professor Sakamoto. The next one is for Professor Chambers about the possibility of applying your method in the larger number of areas.
Okay, thank you very much for your question. It's a very good question. There are two issues here, sort of, that are effectively sort of tied up. It is very large numbers of areas tend to occur mainly in population surveys rather than business surveys. Business surveys, you're tending to be more interested in what I call domains, or in this case, industry groups. And although you may have 40, 50, maybe even 100, it is unusual to have a huge number of them, whereas it's quite different in population surveys. So I was focusing on business surveys. For example, as you saw in that ABI application, there were 28 areas, but the sample sizes ranged from 7 to almost 1,500. So you got some which are very, very small sample size, some which are very, very big sample size. So that's the first thing, is the 40 was sort of like a compromise. The second thing is realistic. You're doing simulations and you're doing it under many, many different scenarios. And you're using code which, as I was pointing out earlier on, can be quite slow. So it's a compromise. You don't want to have too many areas because that would take too long to do the simulations, or you know, so you can have too little. So in theory, the ideas are extendable. can be scaled up, particularly the M quantile, which can scale up very well. But we thought 40 was enough to bring out the message we were trying to get. So that's why, 40 is there, but there's nothing magical about it. We can scale it up.
Thank you very much.
Okay, thank you very much. Since Mr. Anwar is already in, I will give it to Mr. Anwar again. Please, Mr. Anwar.
Okay, thank you, Dr. Bagus. Sorry for troublesome of my connection. So there are another question for Prof. Chamber as well as Prof. Wataru. Or maybe let me read questions from Raden Aurelius. I don't know whether this one has been voiced out or not. Is there any, and this one is for Professor Wataru. Is there any possibilities to use generalized Poisson model? The Poisson model that used in the analysis, Prof. Wataru?
Thank you for your question. About the newest message in the chat, possibility to use a generalized Poisson model for the Poisson model. I think I haven't tried to compute, but I think it is possible to extend to the generalized Poisson model. Probably it's the log if the mean structure is modeled by using the B-sag-Yoke model. So I think it is possible. It would be possible to extend it. Yeah.
Okay, thank you, Prof. Wataru. Hopefully it can answer the question. And then another question is for Prof. Ray Chamber. So actually, I'm wondering whether the bias corrected as well as the bootstrap itself, where we know that generally bootstrap is a bit more on non-parametric approach rather than for parametric approach. How good is actually this bootstrap approach for estimation dealing with the outlier?
It's good point. The bootstrap itself is semi-parametric rather than fully non-parametric. This is the block bootstrap I'm talking about. The reason it is semi-parametric is it makes the assumption that you can generate the fixed effects, if you want to call it, from a model, say the beta, but any between and within area variability that's not explained by your covariates, is handled non-parametrically. So you have this combination of random effects being handled non-parametrically and fixed effects being handled parametrically. So that's why we call it semi-parametric. Mostly the fixed effects, they're not really a big part of the problem with robust estimation. They're easy to solve. It's the random effects, both at the area level and the individual level, that are difficult to handle. And so that's why the bounded block bootstrap in particular seems to be able to handle outliers in those sort of, if you want to call latent variables, much better than an ordinary bootstrap does.
Okay, thank you, Prof. Ray Chamber. Okay, another question is for Prof. Wataru. This is from Muhammad Nur Fikri Adam. The question is there any certain capacity for spatial data observation to be treated with this Poisson method?
Okay, thank you very much for your question. Maybe the capacity means that sample size or the number of regions, the number of areas, isn't it? If so, maybe this is possible. I haven't tried the bigger data set, but it is of course possible, but this is the problem is the computational cost. So I needed to investigate more. Yeah.
So it means you say that there is no limit for the number of observation for this spatial data observation?
Sorry, pardon me, please.
Yeah, I mean, it means there is no limit for the number of observations actually.
Yes, this is I think this is a problem of the computer performance. Yes, and so yeah,
Okay.
theoretically no limit. Yeah, yeah.
Okay, thank you.
Yeah.
Okay, thank you, Prof. Wataru. Then another question is for Prof. Ray Chamber again from Tali Purwa. So the question is how to detect a heteroscedasticity if there are more than one auxiliary variable in the model?
We only had one auxiliary variable, so but the typical way that is handled, certainly in the econometrics literature, is to make the heteroscedasticity a function of the, if you want to call it, the total contribution of the fixed effects. So you take a linear combination of the auxiliary variables and use that to generate heteroscedasticity in your error term. So it is not difficult to bring in, if you want to call it, multiple auxiliary variables into this framework. We didn't bother to do it, but it makes sense in many situations.
Thank you. Very interesting. Okay, another question is because we still have time for another 15 minutes for the Q&A session. So the question is for Professor Wataru Sakamoto. In order to make clusters or mapping, what are aspects to consider to determine the number of partitions or cluster? Prof. Wataru.
Just a moment. What are the aspects to consider? Probably that question. Thank you very much for your question. Probably the question is about what is the meaning of considering 3 or more clusters. But for today's example, the number of areas was relatively small, but that if there are many more number of areas, we could have the several separated clusters. So in that case, we would need to consider the 3 or more clusters. Then, so that is we need to consider our mixture models with 3 or more components.
Okay, thank you, Prof. Wataru. Hopefully, it can answer your question. Okay, please, if the audience want to raise a question, please let me know from the chat room so that we can assign you to raise the questions. Okay, if there is no question yet, maybe a question again from me for Prof. Ray Chamber. Really, I'm also interested in robust statistics. My thesis also on outlier detection as well. But when we combine the outlier detection as well as robust estimation with the small area estimation, so actually, what is the main problem when we combine these two approaches? What is the main problem actually, Prof. Ray?
Okay. I didn't mention outlier detection because the main focus of robust methods is not on outlier detection but outlier accommodation. That means there is no attempt to say, okay, you're an outlier, you're not an outlier, that sort of thing. But if, for example, a value is very large or very small, then it is accommodated in the estimation process. But it is a natural thing that when you have data, you perhaps identify certain values in there which you think are outliers, and then how do you bring those into the estimation process? I personally have not worked very much with integrating outlier detection and robust methods because, as you can see, their purposes are somewhat different. But I would imagine that you would probably use the detected outliers to effectively tune your M estimation method, your robust method. So I'd use it in choosing for extra tuning constants or things like that. So I think there's information in detected outliers that can be used in the robust estimation process. But beyond that, I am not aware of any direct integration. It doesn't mean it hasn't happened. It's just I'm not aware of any direct integration of those ideas.
Okay, thank you, Prof. Ray. Okay, maybe another question is for Prof. Wataru Sakamoto. This is also a question from me. So regarding the disease mapping data, and you're concerned about this, and did you do something to have your method in disease mapping data to be applied for the current big issue in COVID-19?
Yes, I'm very interested in applying to COVID-19 data, and to do so, both spatial and temporal effect should be introduced, and also I would like to challenge. I'd like to challenge to try to make analysis, but I have very little time to try. So if I have more time, I would like to try. Yes.
Okay.
So and my student Septian Rahul Leandro will give a talk after that, and, so about COVID-19 analysis in Indonesia. Yes.
Okay, thank you.
Yeah.
And maybe another question to Prof. Wataru. When you talk about cluster detection, right? Cluster detection for the disease, it seems that the reference is very rare. You mentioned when I saw your slide, you mentioned first article was in 1977. You refer, and then 2005, then 2006, and so on. It seems like there is a jump from 1977 to 2005. So what happened with the development of the cluster detection regarding the disease mapping?
Sorry,
so what I mean here is the reference you refer in one of your slides. So you mentioned first you refer to the article on 1977, and then there 2005. It seems there is no development between the year. So what I mean, what is your comments about that? Especially for the cluster detection.
On the cluster detection. It means probably in 1997 by Karlsruhe, this very famous circular scan statistics, and 2000 means
then 2005.
1990s. So after 2000.
The slide numbers 22. Slide number 22 of
22?
your presentation.
Okay, 22. In Tango and flexibly shaped scan 2005 and
yeah, correct.
And yes.
So there seems not any yeah.
So actually, I'm not sure about the development on scanning methods between these two.
Okay, no problem, Prof. Wataru. Yeah, because I'm wondering maybe there was no development within the year, within the period.
Yeah, yes, but
Yeah.
yeah, many. I think many other small changes, but
Small changes,
I'm not
maybe
sure about the
small
detail.
development only.
Sorry.
Okay, thank you. No problem, Prof. Wataru. Okay, another question is for Prof. Ray Chamber just now. So from Ms. Dian Handayani, M quantile model do not depend on strong assumption on distribution on variable of interest. Is it still necessary to make to make a logarithm transformation for the variable of interest, which has a skewed distribution?
Right. No, it's not necessary. We did it because the models, effectively the M quantile fits, appeared more realistic on the log scale. Remember, we were using linear M quantile models. Okay, and so you want to basically fit these on a scale where linearity makes sense. And that's essentially the log scale with these data. This is economic data, financial data. So you can fit linear models on the raw scale, but obviously there would be questions about whether that's a reasonable assumption at the raw scale. I don't think anybody would argue that on the linear scale, looking at the data, they'd say, yeah, linear model here for the M quantiles is a reasonable thing to do, which is why we went in that direction. But we could have stayed in the raw scale and we got similar results. It's just that we decided to present it on a log scale because it was just as easy to do.
Okay, so maybe continuing to the previous questions, did you do any concern about whether the distribution is skewed or highly skewed like that, Prof?
Sorry, did we take any, sorry, was that me? To me? A question?
Yeah, I mean, if you talk about the skewed distribution,
yes.
Is there any concern about whether it is skewed only or highly skewed distribution?
Well, in our simulations, we used distributions which were quite highly skewed, with outliers coming in on the right tail, very far out. We didn't investigate. It doesn't matter as far as our techniques are concerned, whether you're dealing with something which is skewed or highly skewed, except in the context that when you're truncating, your tuning parameters will obviously reflect to some extent that type of knowledge. You may remember at one stage I said we used a tuning parameter of C equals 3
Yes.
when we were Huberizing. And I said, that's not necessarily the best for this type of data because it is so skewed. In fact, we have done experiments with C equals 6 and C equals 9, and they do perform better. But I just gave these results, well, I had them there, and they're in the paper that will be published sometime this year. But no, I think, this is where you need to think about, in some sort of sense, how you model this is not modeling outliers, but certainly modeling robustness to the outliers and thinking of how you choose the tuning constant, and that depends on just how bad the situation is in your data set.
Okay, it's very clear. Okay, another question for Prof. Ray Chamber, just now coming in from Muhammad Nur Fikri Adam. Does the data which have parametric characteristics have the potential to be treated with bootstrapping method?
Ordinary, I assume you mean ordinary bootstrapping, just simple resampling of the data. You can certainly apply bootstrap to anything. Whether it'll give you realistic results is another matter entirely. I think I had a slide somewhere, I'm just looking now on my, I had a slide which commented on that. I think it's, I think it's slide 22. If you have data which is highly skewed, so you've got many outliers, remember, the bootstrap will generate too many outliers because you're resampling from the sample. So you'll be generating lots of outliers. So you will have a very, your bootstrap distribution will not look like the real sampling distribution. So in that sense, you've got to be careful bootstrapping with outliers. And this is why we're using the bounded block bootstrap in this situation. We're trying to control that behavior of the bootstrap. You can technically apply the bootstrap to anything. It's just whether it'll work or not. That's the matter.
Okay, good. Okay, continuing to the previous question regarding the bootstrap, Prof. Have you tried to do like a jackknifing for this problem?
No, we haven't tried jackknifing. It's again, you can see the problem. You're jackknifing. What you're doing is you are perhaps throwing out you're throwing out one observation. Let's say you jackknife with one observation less, right? You're throwing out one observation at a time. Let's suppose you've got 2 outliers or 3 outliers. You throw one of them out. You still got 2 in your sample, and so your jackknife is not going to work, is it?
Yeah.
Because it's going to blow up. No, I think we looked at it and thought, no, the jackknife idea is not the right idea here.
What about jackknife delete 2, for example?
You don't know how many. This comes back to the question: how many outliers are there?
Yeah, correct.
So you've got to be careful.
Yeah, that's correct. Okay, maybe if from the audience, if you have another question, we still have another 2 minutes to cover. If you have another question, please welcome.
Can I ask a question for Professor Sakamoto?
Yeah, please.
Okay.
I was curious. I mean, really nice ideas.
Thank you very much.
Really nice. I was just wondering, I'm sort of used to dealing with SAR type models, not a Bayesian approach, but a more frequentist approach, SAR type models, also with spatial network type structure. So I was just curious as to have you ever explored, or you know anyone who's explored this idea of if you want to, I refer to it as bump hunting. You're looking for exceedances, right? These are your clusters, right? You're looking for where things go big, but they're all big together. Have you tried applying some of these SAR type models with to the data you have? I was curious because I think it's very important to find these clusters of large values.
Thank you.
Please, Prof. You can directly answer.
Yeah. But as a matter of fact, I can't catch the detail. Would you, if you're okay, would you later would you email?
Yeah, sure. In SAR more simultaneous autoregressive models, right? SAR. The
SAR model.
SAR, simultaneous autoregressive.
Sorry, pardon me. Sorry.
Okay, maybe we'll leave it till later because I think there are issues with audio over here.
Yeah, correct. Maybe Prof. Ray, you can send email to Prof. Wataru later.
I'm curious. I will.
Yeah. Thank you. So anyway, thank you very much for Prof. Ray Chamber and also Prof. Wataru for your valuable time for this conference. So we will give you some token appreciation. So I give the time again to Master of Ceremony. Thank you.
Thank you very much.
Thank you.
Yeah, please, MC, you can have your time.
We thank you, Dr. Anwar Fitrianto, already lead the panel session 1, and one more time, big word of thanks to both of you, distinguished Professor Wataru Sakamoto from Okayama University of Japan, for your sharing under the title Analysis of Disease Mapping Data, How to Detect Cluster of Higher Prevalence More Flexibly. And either to you, Professor Ray Chambers from University of Wollongong, Australia, for sharing the subject outlier robust small domain estimation via bias correction and robust bootstrapping. You're both sharing this morning very enlightened to our knowledge. Ladies and gentlemen, we have listened very attentively to very thought-provoking presentation. It's very informative indeed. And we now invite Head of Department Statistics to deliver the token of appreciation and the certificate to both the invited speakers, either to the moderator. We welcome you, Dr. Anang Kurnia, MSI.
Okay, thank you for the time. Prof. Wataru and Professor Rai Chambers, I thank you for your contribution in the conference. I think an inspiration topic where you deliver for in this morning. Yeah, but I'm sorry we cannot meet in person in Bogor. I think maybe some time we will invite you, Professor Rai and Professor Wataru, to come in Bogor sometime, I think. In this time, we say thank you and we present a token appreciation for you, Professor Rai and Professor Wataru. I think we hope you like it. This is for you, Professor Wataru. And then please
Thank you very much.
In the background is batik, Professor Wataru. Indonesian khas from Indonesia. And then please for Professor Rai Chamber.
Oh, very good.
Very nice. Thank you.
My wife will be very impressed.
Okay. Okay, thank you, Professor Rai, and also thank you to Pak Anwar Fitrianto. We will say thank you for you as chairman in this session. Thank you, Pak Anwar, and we back to the MC. Yeah, this is for Pak Anwar.
Thank you, thank you.
Okay, thank you very much. Thank you, Pak Chambers and Pak Wataru, and also Pak Anwar. Thank you very much.
Thank you, Anang.
Yeah.
Thank you.
Thank you very much.
Thank you, Anwar.
Professor Kanya.
Thank you, everyone.
Thank you.
Thank you
very
to
much.
Dr. Anang for delivering the token of appreciation for the three honorable speakers. Distinguished guests, ladies and gentlemen, as mentioned on the program book, by 11 hours, we now come to the parallel session 1. There will be 6 topics to discuss in 6 different rooms. Ladies and gentlemen, kindly rename your ID name on your each screen.